Good morning to one and all. I am Dr. Tirupataish Kasani, Assistant Professor in the Department of Mechanical Engineering at School of Engineering and Technology, Adamas University, Kolkata, India. And today I am here to discuss about the unconventional machining processes. Okay, before going to what is machining and what is machining process, first we will try to understand what is a manufacturing process. Manufacturing process as manu means hand, factors means to make, means manufacturing means to make the components using hand. That is nothing but the manufacturing process. Means machining process is one of the category of the manufacturing process. Okay. Now we will see the contents of this course or this module. This is unconventional machining process. Here are the contents. It will follows the introduction, working principle, material removal mechanism, applications, advantages, and disadvantages. First, we will start with the introduction part. That is, what are different types of manufacturing process? Means we can categorize the manufacturing processes broadly into casting, joining, forging, and machining. In this, the first one, the casting, wherein the molten metal is allowed or poured into molten cavity, and we are allowing that molten metal to solidify as per the shape and size of the mold cavity that is created to get the final product. Okay. And the next one is the joining process, wherein we can join two or more metals. For example, welding is the permanent kind of joint, and screws, nuts and bolts will be the temporary joining process. Of course, we can consider rivet joint also. And the next one is the forging process. Forging process is a kind of manufacturing process wherein the metal will be subjected to the compression force or elastic elongation force. Means either tension or the compressive forces. The metal is subjected either at the room temperature or at the higher temperatures. Means depending upon the type of material what we are using. For example, if we consider the steel, to make the to work over the steel, to change its size and shape into desired shape, we are going to heat the metal to the elevated temperatures. So for example, above the 600 or 800 degrees centigrade. After converting that iron into red hot state condition, we will try to apply some compressive nature of forces to get the size and shape of the component what we require. And the next one is the machining process. This is the machining process wherein the metal will be removed from the bulk material or the raw material in the form of chips using a cutting tool. For example, if we look at the definition of the machining process, the process of removing the excess material in the form of chips with the help of sharp cutting tool from the raw material to get the desired shape and size of the component. Means there is a component, then we will try to extract the material from that in the form of chips. Now we will look into the conventional machining process, wherein direct contact and relative motion between the workpiece and the material, workpiece material and the tool are a must. For example, if you consider this lathe turning, drilling, milling. If you look at this, for example, let me open this pointer options. This is the laser point. For example, this is the lathe turning. For example, this is the lathe turning. This is the workpiece. This is the direction of the workpiece that is rotated after mounting in the 3-jaw or 4-jaw chuck. And this is the tool. This is the cutting tool. Cutting the feed motion will be like this in this direction along the axis of the rotating workpiece. And this is the chip that is removed from the work material. This is the machined surface and this is the unmachined surface. And this is the cutting tool. Means this material which is removed out from the raw material or the work material, we can call it as chips. Means in the form of chips. Okay. And another kind of machining process, here it is the drill bit or drilling. Here it is the drill bit. This is the feed motion of the drill bit into the workpiece. This is the rotation of the drill bit. Means after removing the material in the form of chips, those chips will be ejected out through the flutes. These are called grooves or the flutes over the drill bit. The chips will be coming out through those grooves, and we will remove the we will remove using brush or the compressed air from the machining zone. Why? Because if the chips will be remain at the machining zone, then that will damage the machine surface. Similarly, the C and D, that is the milling. These two are the milling cutters. Means this is a peripheral cutters. Means peripheral milling cutter. The teeth will be located on the periphery of the rotating element. Okay, and here it is the end mill cutter, wherein the tooth or the cutting teeth will be located at the end portion of the rotating element. These two means this is the direction of the rotation of the milling cutter, and this is the slab. This feed motion or the workpiece motion will be like this, and this is the rotating. Means the chip flow will be here. Means the chips are ejected out here in this portion. Okay. Here in this case also this is the work, and this is the rotation of the milling cutter. Okay, and this is the machined surface, and this is the unmachined surface. Okay, due to this rotation, the cutting edges will come in contact with the raw material, and the chips will be ejected out. Small chips will be ejected out, and we will try to remove this. Means here in conventional machining process, the direct contact in all these four cases, the direct contact of the workpiece and the tool are must. That is the reason why we can call this as conventional machining process. Then what is unconventional machining process? We can call unconventional machining process or non-conventional or non-traditional machining process. Okay, in this unconventional machining process is a special type of machining process in which there is no direct contact between the tool and workpiece. Means here there is a direct contact. Here no direct contact between the tool and the workpiece. A form of energy is used to remove unwanted material from a given workpiece. Means how it will be. These are the examples of the different non-traditional machining process. Okay, in this module we would like to cover all these. Okay, for example, here it is the abrasive jet machining process. This is the ultrasonic machining process, and this is the laser beam machining process, and this is EDM, electron discharge machining process, and this is the electron beam machining process, and this is plasma machining process, plasma arc machining process. Means we will try to understand what is this unconventional processes with different kinds of applications, with the different what are the advantages and disadvantages associated with each of the machining process. Okay, down the line. Now we will see one by one. First, we will start with the abrasive jet machining process. We can call this as AJM process. Okay, this is the schematic of the abrasive jet machining setup. Okay, wherein here this is the air compressor. This is the air compressor, means to compress the air, and this is the turn valve. Turn valve means to open and close the valve, means to release and stop the gas from the compressor cylinder. And after releasing, the gas will be flowing through the pressure control valve. Means we need to maintain some amount of pressure for different machining process while machining different types of materials. Depending upon the material, we can choose this pressure, how much it is to be maintained for the flow. After after the pressure control valve, it will move to the dryer. The purpose of this dryer is to remove the ambient air. Ambient air generally consists of the vapor, right? That vapor means whatever the moisture content that will in the air which is available in the ambient air will be removed using this dryer. Means moisture content will be removed here, and then it is further fed to the filter, wherein any fine particles of the dust will be there, then it will be removed by this filter, and then it is fed to the mixing chamber. Okay, what is this mixing chamber? What are the elements that are going to mix in this chamber? Means, as the machining process name itself is indicating, abrasive jet machining process. Okay, abrasive, abrasive particles, different types of abrasive particles. As you know, abrasive particles are having multiple cutting edges. For example, Al2O3, B4C, SiC means ceramic powder. Means we can use different types of abrasive powders are the particles of different sizes depending upon the material size and what is the type of material that we are using. Means these abrasive powders will be mixed through this mixed in this chamber with the dried hair, pure and dry hair. Okay, dry air and this abrasive powders, means these abrasive particles and the dry air both will be mixed in this mixing chamber. Okay, how these will be mixed? Using the electromagnetic shaker. Okay, electrical energy, magnetic energy. This is the using the electrical energy is the supply energy is supplied to this. Okay, magnetic field will is induced, and that electromagnetic energy will be used by this equipment, that is electromagnetic shaker, to mix the air and the abrasive particles, and the thoroughly mixed air and the abrasive particles are fed to the nozzle. This is the nozzle. Means abrasive mixed with the carrier gas. We can call this dry air as the carrier gas. Okay, it is now mixed with the abrasive particles. Now it is fed to the nozzle. See here, there is electromagnetic on off valve. Means to control the control the mixed air. Means mixed air and the abrasive particles. To control the flow of that, this is the valve to control the flow. And this is the nozzle finally, and this is the workpiece where we would like to remove the material in some shape, so that we can get some shape over the top surface of the workpiece. Means the velocity, the pressure of the abrasive particles, which is already mixed with the air, will be controlled by this valve. If I release this valve, then the air along with the abrasive particles will flow through this nozzle and it will hit the top surface of the workpiece. Of course, the workpiece will be mounted over the table. Okay, here it is the screw and pinion mechanism to for the feed motion of the workpiece during the machining process. Means we need to move the workpiece material to and fro. Means the nozzle position is fixed here, then we will try to move the workpiece relative to the nozzle, so that at the specified regions we are trying to remove the material using this abrasive jet, high speed and high velocity abrasive particles. Means these abrasive particles are having multiple cutting edges. Those will come and hit the top surface of the workpiece, and that is the reason why the brittle fracture will occur, or I can say the erosion of the abrasive particles over the top surface of the workpiece with the material, that causes the removal of the material from the workpiece. Okay, after this, here it is the exhaust. Means after impinging the abrasive particles, those will be falling down, and whatever the gas will be escaped out into the ambient from this exhaust valve. Okay, and now here we will see it is the material removal process, where the material is removed by a high velocity stream of air or gas mixed with the abrasive. We have already seen this is the mixing chamber. This is the air, and the abrasive particles will mix and will flow through this nozzle. And what is the working principle? A focused stream of abrasive particles carried by high pressure air or gas is made to impinge on the work surface through a nozzle. This is the nozzle, and the work material is removed by erosion by high velocity abrasive particles. Means the working principle is this. Means when the high velocity abrasive particle hits the top surface of the workpiece material, due to erosion, the material will be separated out from the workpiece in the form of chips. Those will be taken away by this flow of the air from the machining zone. This is the mechanism of material removal, is the erosion in this abrasive jet machining. Okay, and the typical material removal rate we will use this we will indicate this with MRR. Okay, the typical material removal rate will be 1.8 to 5.8 mm³ per minute. That is the typical values. That is not the standard. Okay, and here it is the abrasives. What are different types of abrasives that we can use in this AJM process is aluminum oxide Al2O3, silicon carbide, sodium bicarbonate, dolomite, and glass beads. These are few. There are others. Okay, there are other abrasive particles also used depending upon the material used and depending upon the size of the material used. Okay, and next, we will see how this is the nozzle. This is the enlarged view of the machining zone. Means this is the region where abrasive particles will mix with air and it will come and it will hit the workpiece. This is the workpiece and this is the nozzle. See here, these black color dots are the abrasive particles. When these particles will come and hit this, due to the erosion, the metal or the workpiece will be separated out and it will be moving like this outside. Okay, of course, this is the high velocity, high pressurized gas mixed with the abrasive particles. Means the kinetic energy of the abrasive particles is converted into tearing action of the material on the top surface of the material or the workpiece. Okay, here it is the distance between the nozzle tip and the top surface of the workpiece. We can call it as standoff distance. The typical value will be 0.5 to 15 mm. That will vary from the material to the material, and what is the size of the groove that we need, and what is the size of the machining area we require at the top surface of the workpiece. All this will vary. Means this D will be 0.2 to 0.8 mm. This is the DI. Okay, and this is the nozzle. This is a high velocity abrasive gas jet, that is 150 to 300 meters per second. These are the typical values. This di is the diameter of this nozzle tip. Okay, and this is the standoff distance. This is the schematic of material removal. When it comes to the effect of the NTD, what is this NTD? Nozzle tip distance. Nozzle tip distance in abrasive jet machining process. See here, this is the nozzle, this is the nozzle. If there is no workpiece, then the stream of the abrasive particles along with air will flow like this. Means from starting point, means from the nozzle tip, when it goes down, it is bulging or it is diverging. The stream will be is diverging. Means if the standoff distance or the NTD nozzle tip distance, NTD or the standoff distance, both are the same. I can say if the standoff distance or NTD is increasing 0.75, 1, 1.5, 2 mm. Okay, see here, this is the 0.5 mm width of the material is removed here. When it comes to when the NTD is increasing to 1 mm, zero point 0.7, the width is also increasing. Why? Because here it is diverging. Means the top side surface of the workpiece material, as the distance NTD is increasing, as the distance NTD is increasing from 0.75 to 2 mm, the top surface of the workpiece, which is exposed to the stream of these abrasives and air, is also increasing. That is the reason why 0.5 to 0.7, zero point 0.7 to 1, 1 to 1.5. Means the machining area or the region is also increasing. However, the effect is different for different standoff distances or the NTD distances. Okay, means if I need a precise hole like this, I can maintain the NTD as lower distance. If I need some curvature surface or larger area from where the material can be removed more, then I can maintain this NTD or the standoff distance as 2 mm. Okay, like this. Means if the NTD or the nozzle tip distance or the standoff distance will vary, the machining area or the machining zone region is also varied. What are different types of applications? What are various types of applications of this AJM process? Applications include roasting of glass, means machining of the glass, and cleaning of metallic smears on ceramics, oxides on metals, resistive coatings. Means for example, corrosion resistant coating or some materials or some metals. Okay, after use of some time, at some portions the resistive coating may be peeling off. Okay, to remove the remaining coating, we can use this type of machining process, abrasive jet machining process. Okay, here it is the drilling of the glass wafers, wafers which are having very less thickness, and deburring of the plastics. After the machining of the plastics, some portions of the plastic will be stick to the bulk material only. To remove those burrs, means deburring of the plastics, we can use this. And permanent marking on rubber utensils, for this also we are using abrasive jet machining. Engraving registration numbers on toughened glass used for car windows. Okay, engraving registration numbers. Nowadays we can see in the society that few cars, high-end cars, okay, these are making the numbers using this technique only over the glass. And for cutting thin fragile components, germanium or silicon, etc., means fragile in nature, the materials which are fragile in nature. And finally, for drilling, cutting, deburring, etching, and polishing of hard and brittle materials, we will use this abrasive jet machining. Means here we can control the velocity of the flow and the pressure of the air and the size of the particles, and we can control this standoff distance, and we can control this nozzle diameter, okay, etc. These are the process parameters. Means depending upon the material, depending upon the process, we can alter these process parameters. Okay. uh, and now what are the advantages? What are the advantages of abrasive jet machining? A high surface finish can be obtained depending upon the grain sizes. Depth of damage will be low. That is, depth of penetration will be 2.5 microns. It provides cool cutting action, so it can machine delicate and heat sensitive materials. The process is free from chatter and vibration. All of you know the chatter is the vibration phenomena, that is common phenomena in a lathe machine when we are machining or turning a long higher slenderness ratio rods. Okay, as there is no contact between the tool and the workpiece. Vibration, as there is no contact between the tool and the workpiece. Here it is, capital cost is low and it is easy to operate and maintain abrasive jet machining. The capital cost means only the hardly the cost of the procurement of those abrasive particles. Of course, if there is a compressor, we can compress the air at any point of time depending upon the flow rate, means how much pressure is required and how long it is required. Okay, the capital cost is relatively low for this abrasive jet machining. It has the capability of cutting holes in intricate shapes in hard materials. Okay, but because the material removal phenomena is the erosion. Here it is the disadvantages. Abrasives may get embedded in the work surface. Means, as I told, the abrasive particles are having multiple cutting edges. If the workpiece is ductile enough, the abrasive particles may hit and may clog there, may stuck there over the top surface of the workpiece. Okay, means may get embedded in the work surface if the workpiece material is ductile or the high toughened material, especially while machining soft materials like elastomers or soft materials. The accuracy of cutting is hampered, means the accuracy of cutting is altered by tapering of the hole due to unavoidable flaring of the abrasive jet. Flaring of the abrasive jet means this enlargement or the divergence of the stream from the nozzle tip to the downwards. And here it is, the stray cutting is difficult to avoid. Means stray cutting, as we have seen, as the standoff distance is increasing, the stray cutting means the side portion of the machining zone, okay, means the material removal zone is increasing along with the standoff distance or the NTD distance. That is, stray cutting is difficult to avoid. Means due to the divergence of the stream, it is unavoidable or the difficult to avoid the sides cutting. Okay, and here it is the nozzle life is limited. Why? Because 300 hours. The typical life of this nozzle is 300 hours. Of course, if we use the advanced nozzle materials, we can increase further the life of the nozzles. And abrasive powders cannot be reused as the sharp edges are worn and smallest particles can clog the nozzle. Why? Because here it is the after impinging the abrasive particles on the top surface of the workpiece, the chips, those are small in nature, and those will be mixing up with the abrasive particles. Okay, that is one disadvantage. And the cutting edges will be worn out easily. Means before using the abrasive particles again, we need to separate out the chips and we need to sharpen the abrasives particles cutting edges. Okay, otherwise these may clog the nozzle. Okay, and the next one will be the ultrasonic machining process. What is this ultrasonic machining process? See here, schematic of the ultrasonic machining process setup. Ultrasonic machining setup. Here we will start with this. This is the ultrasonic oscillator. You know that the ultrasonic, whenever there is a power supply, then see here, this is the ultrasonic waves of high frequency. Whenever we are giving a power supply to this ultrasonic oscillator, then we will whenever we are giving power supply to this ultrasonic oscillator, this is the ultrasonic transducer. This is the excitation coil, and these are the leads or the power connections, and this is the feed mechanism. Whenever this power supply will be given to this ultrasonic oscillator, this ultrasonic transducer is vibrating, or means enlarging and contracting, means elongation and contraction of this due to the power supply. The ultrasonic transducer will be oscillating, uh, oscillating with higher frequencies depending upon the frequency of the power supply that we are providing. This is the transducer cone or the horn. This is the transducer cone or horn. This is the connecting body. This is the tool holder, and this is the direction of tool motion, and this is the cutting tool. This is the actual cutting tool. Okay, if you observe, means whenever power supply is given, this is trying to oscillate in this direction. Okay, ultrasonic with high frequency. It means here the frequency of this material will be very less, very high. Frequency is high, but the amplitude is very less. Okay, high frequency but less amplitude. To enlarge this amplitude, we are using this connecting body transducer. Means this oscillation motion is amplified using this connecting body transducer and the transducer and the connecting body. With these two, means tool holder will be used to hold this tool, and this is the direction of the tool motion. Means direction of the tool will be like this. Okay, this is the tool, and this is the workpiece and the fixture and the table. Of course, there is a movement for the table to move in x and y directions. Okay, for the table movement, means to move the workpiece. Why? Because here also the tool position will be fixed. Why? Because this is the high equipment or the high setup. Okay, robust in the construction, and it is easy to move the work table than this whole setup. Okay, and here it is the reservoir, and this is the abrasive slurry. Earlier, the abrasive particles in abrasive jet machining process, the abrasive particles are mixed with the air, the dry air. Here, sorry, the abrasive particles are mixed with the water. We can call that as abrasive slurry. Means with the water, the abrasive particles are mixed, and this is the circulating pump. This pump will be supplied to the refrigeration system. Okay, through this will be fed to the machining zone. This is the machining zone. This is the abrasive flow. Means the refrigeration system means actually the pump and this refrigeration system will helps in controlling the supply of this slurry to the machining zone. Okay, here this is the machining zone. Means after supplying this, actually this is the flat surface before the machining process. Means the power supply is given, it is vibrating with higher frequency with low amplitude, and it will be amplified using this transducer, and now this is oscillating in this direction with higher amplitude, and this tool also vibrating, or the amp are also is also moving in this direction, top and bottom. Okay, up and down like this in this motion. Whenever this slurry is come in between the gap, in the gap between the workpiece and the tool, whatever the abrasive particles, okay, those are hit by this tool. Means the tool will hit the abrasive particles, and those abrasive particles will hit the workpiece. Okay, so that so that the kinetic energy of those abrasive particles will be used to remove the material. Of course, after removing the material from the top surface of the workpiece, that will be removed from the machining zone due to this slurry flow. Okay, this abrasive slurry flow, that is water with high pressure and velocity, it is moving from here to here. The chips are extracted out from the machining zone. Means the abrasive particle first hidden or hit by this tool, again that abrasive particle will come and hit the top surface of the workpiece. Okay, that is the reason why the material will be removed out in the form of chips. For example, if we enlarge this machining zone, see here, this is the transducer, this is the tool motion, this is the sonotrode. I can call this as the transducer, and this whole thing I can call it as sonotrode. Okay, including this tool. Here we are saying transducer, connecting body, tool holder, and the cutting tool. Okay, all of these I can call it as a sonotrode. In one single setup, with a single term, I can say sonotrode. This is the tool motion with high frequency, less amplitude. But here the sonotrode amplitude is more than this. Okay, here it is like this. This is the amplitude, but here it is the considerable amount of amplitude length. Okay, this is the workpiece and this is the slurry. See how the abrasive particles, these are the abrasive particles. This is the slurry consisting of. See here, these are the removed particles. Means the flow direction will be like this. The slurry is coming like this. When it comes to here, this tool will hit the abrasive particle and it will come and it will hit the workpiece. And the workpiece material is removed. Small amount of material will be removed in the form of chip, and from here the chip along with the abrasive particles will be moving out, and again this will be refreshed. Means the chips will be removed, and again a fresh abrasive particles or the sharp edged abrasive particles are again mixed in this reservoir or the tank, and again it is supplied to the machining zone to continue the machining process. Okay, see here, what is this ultrasonic? Waves of high frequency. The ultrasonic machining process is suitable only for hard and brittle materials like carbides, glass, ceramics, silicon, precious stones, germanium, titanium, tungsten, tool steel, die steel, etc. Okay, all these are the hard materials. All of you know that this glass will be machined using this ultrasonic machining. Means making the holes in glasses is possible using this ultrasonic machining. Okay, these are the carbides. All of you know, these are the carbide tools which are carbides used for the cutting tools. Generally using lathe. Okay, using lathe, we can remove the material. The cutting tool materials are made up of carbide. That is generally the tungsten carbide, silicon carbides, etc. Okay, and here the working principle in this machining method, a slurry of small abrasive particles is forced against the workpiece by means of a vibrating tool, and it causes the removal of metal from the workpiece in the form of extremely small chips. Okay, this is the slurry flow from here to here, here from here to here. Mechanism of material removal is brittle fracture or abrading action. Brittle fracture means, for example, here it is the brittle materials like carbides and glass. These are the brittle in nature. That is the reason why brittle fracture or abrading action, another name of it. That is the material removal. Here also, the typical material removal rate is the 15 to 20 mm³ per minute, and the abrasives used are same as earlier: aluminum oxide Al2O3, silicon carbide SiC, boron carbide B4C, and the diamond particles. Here it is ultrasonic machining parameters or the process parameters and the applications. What are different types of process parameters? Earlier in abrasive jet machining, NTD and the nozzle diameter, particle diameter, and the air pressure, airflow, these are the process parameters. Similarly, here also abrasive slurry, abrasive grains plus water content is 20 to 30%, and the vibration frequency 20 to 30 kilohertz, and the amplitude 25 to 100 microns is the tool motion or the movement of the tool. Here it is the wear ratio 1.5 is to 1. Wear ratio, what is wear ratio? Material removed from workpiece to the material removed from the tool. Okay, why? Because here when the tool will come and hit the abrasive particle, if the tool material is made up of copper material that is ductile in nature, that is also when the sharp cutting edge abrasive particle will be hidden by this ductile material tool. Okay, there may be some removal of material of the tool also. Okay, means a small amount of material will be removed out. Why? Because there is an impact of the tool, means a sudden contact or the with high pressure, the tool is hidden by this abrasive particle. Okay, in turn the abrasive particle will go and hit the workpiece material to remove the most of the material from the workpiece. Okay, that is the reason why material removed from the workpiece is 3 times, material removed from the tool is 2 times. I can say 1.5 is to 1. Surface finish: after the machining process, after removing the material from the workpiece, the surface finish is around 0.2 to 0.7 microns, and the tool material being tough and ductile wear outs at a much slower rate. Okay, if the material is highly ductile, okay, if I am using the tool material with a high ductile material, then the wear rate we can minimize. Wear rate is less. If it is hard material, the tool will be wearing very fast. The shape of the tool correspond to the shape to be produced in the workpiece. As I know, as as we have seen already here, this is the rectangular shape of this. Okay, and the same shape of the cavity will be created over the top surface of the workpiece. Similarly, in abrasive jet machining also. For example, if I would like to create a curved surface, then initially I'm creating the curved shape like this type of tool, so that I can create in the workpiece also this type of cavity. Okay, yes, the shape of the tool and the shape of the cavity that you want to create or the remove the material in the cavity is also same. Means the shape of the tool and the created cavity both are same. Here it is the applications. If you see, the precise and intricate shaped articles can be machined. Okay, precisely we can control the all these parameters to remove the material from the workpiece in a precise manner. Holes as small as 0.1 mm can be drilled using this ultrasonic machining process. It is effectively applicable. It is effectively applied to machine glass, ceramic, tungsten, precision mineral stones, etc. Okay, it is used for making tungsten carbide and diamond wire drying dies. Okay, these are the in forging process. This is wire drawing operation. those dies will be made machined using this ultrasonic machining, and dies for forging and extrusion process are also machined using this ultrasonic machining process. What are the advantages of this ultrasonic machining process? It is applicable to both conductive and non-conductive materials. Why? Because there is no power supply to the workpiece directly. Okay, only this vibration motion of the tool will be transferred to the abrasive particles, and those abrasive particles will hit the top surface of the workpiece to remove the material. Okay, mean irrespective of the material conductivity, this machining process we can use it for any type of material suitable for very hard or brittle materials such as graphite, glass, carbide, and ceramics. We have already seen. And USM is used for machining semiconductors such as silicon, germanium. All of you know that the semiconductor material silicon and germanium. These are doped with, okay, and there is doping system, PN junction diode, all are different. USM doesn't produce abnormal electrical, thermal, or chemical abnormal surfaces. Why? Because if there is an electrical power supply to the workpiece, okay, due to this slurry, okay, this slurry is directly coming in contact with the workpiece, the machine surface may be affected. For example, if the heat will be induced more, okay, at the machining zone, then the machine surface may be affected. But here the amount of heat produced during the machining process is very less, and that if at all any heat is produced, that heat energy is taken away by this water, that is slurry medium. And here it is the chemical abnormal surfaces. See here, there is no chemicals are involved, only water and abrasive particles. If the chemicals are involved, if I am using this some chemicals in the form of slurry, then the machine surface may gets affected. Can drill circular and non-circular holes in a very hard materials. Okay, less stress because of its non-thermal characteristics. There is no high amount of heat generations at the machining zone. And when it comes to finally, when it comes to the disadvantages, USM has lower material removal rate. Why? Because here also we can control the size of the abrasive particles. Okay, here also same standoff distance we can control. Okay, and fast tool wears fast in ultrasonic machining. As I already told you earlier, the tool, if it is a ductile material, we can improve the life of the tool. Machining area and depth is restrained in USM, ultrasonic machining. That's it. Thank you. We'll meet with some other topic in the next class.